our next example is another classic calculus question. It says a 6.5 meter long ladder leans against a wall, and if the foot of the ladder slips outward at a rate of 1 meter per second, find the rate at which the top of the ladder is descending the wall at the instant the foot is 2.5 meters from the wall. So at first glance we have that. So if you want to just pause the video for a second to copy that down, feel free. But what I'm going to do is show you another video of exactly what I'm talking about. And now this is a little demo with a small one, but you'll get the idea. So here we have somebody set up a little mini ladder against a mini wall, but we'll see what we're talking about. We know it's going to slide down the wall. So the bottom is going to start to slide out and the top is slipping down. So if we know how fast this is falling out, how fast is this slipping down? So how fast is the bottom going or how fast is the top going as the bottom is falling out? So as this falls out, how fast does this fall down? That's what this question's asking. So we have a 6.5 meter long, we know how long that is. The foot of the ladder is slipping outward at a rate of 1 meters per second. Find the rate at which the top of the ladder is descending down the wall. So how fast is it falling down the wall? So we're going to need to draw a picture here. Again, these pictures are really, really helpful to try and visualize what's going on. So here's the wall, and we have some ladder. Again, I encourage you not to get distracted by the awesomeness of my pictures. And we've got this along the floor here. We've got a couple of known variables here. We know the 6.5 meter ladder is right here. So we know that that is 6.5 meters long. We also know that this dimension here is scooting that way. It's moving outward at a rate of 1 meter per second, 1 meter per second. And we would like to know how fast it's going down. So we want to know that part. How fast is that side going down? And remember that speed is dependent on when we're talking. So we sort of freeze the picture at a certain time at the instant when the foot is 2.5 meters. So right here is 2.5 meters from the wall. Okay. So again, it's important if we start with our list of what we know. And to do that, we need some letters here to help us. So I'm going to use L for the ladder. So I'm going to use this side as L. And I'm going to call this side X, simply because it's on the horizontal, and I'm going to call this side Y. So X actually represents how far it is here, and Y represents how far it is here, and then L would represent how long the ladder is. So we have all those known variables or unknown variables, and we have their corresponding related rate. So I'm going to start by looking at L. So L is one of my variables, and I know that the ladder is actually 6.5, so I know that one is 6.5. As I write down a variable, I'm also going to write down the related rate. So dL by dt, how fast is the ladder changing with respect to time? Now in this question, if you just stop and talk to your elbow partner for a second, how fast is the ladder itself changing with respect to time? So hopefully you and your elbow partner have talked about this and realized that the ladder's length doesn't change. It stays the same. So because the ladder length doesn't change, dl by dt is actually 0. It doesn't change. It stays the same way. That doesn't say it's 0 meters. It says it doesn't change. So the derivative of the related rate is 0. Now we've got other variables here. We've got x on the bottom. At this particular snapshot, x is 2.5. And then we have its related rate, dx by dt. And we do know that. How fast is x changing? Well, it's changing at 1 meter per second. So dx by dt is 1. And we have another variable here, y. And we don't know that yet. So again, we may or may not need to know that. We don't know how high it is here. We might be able to figure it out, but we may not need to know that yet. And then its related rate, dy by dt. And this is my unknown. I want to know the rate at which the top of the ladder is descending down the wall. So how fast is that going down? That is dy by dt. Okay. So now I'm going to look at this. This isn't an area question. It's a different question. At this stage, we have to figure out some sort of equation or formula that has all these variables in it. So I'm going to give you a second to talk to your elbow partner if you have any ideas of an equation in this scenario that would have variables L, X, and Y in it. So I'm sure you all have had a chance to talk to your elbow partner, and hopefully you've discovered that one variable that we know that's really good in this scenario is Pythagoras' theorem. Okay, we do have a right triangle here, and we have the hypotenuse and its two sides, so we can use that. So let's do that. So I'm looking at L squared equals x squared plus y squared. That equation has an L, an x, and a y in it. And I know that Pythagoras is L squared equals y squared, x squared plus y squared. You could have it the other way around. That would be totally fine. I just decided to write it this way. All right. So now that I have that, I need to differentiate it with respect to time, because the things I need are dl by dt, dx by dt, and dy by dt. So I'm going to differentiate this with respect to time. So there's no t in here, so everything's going to need to have that d something over dt. The derivative of L squared is 2L, dl by dt. The derivative of x squared is 2x, dx by dt. And the derivative of y squared is 2y, dy by dt. So the implicit differentiation, it comes in really handy here. In fact, we couldn't use any of the other types of differentiation at this point. So this question needs explicit differentiation because we don't even have a t in there. So we talked yesterday about the need for implicit differentiation. You need it here. There's no other way we can differentiate with respect to time. So now I'm going to go through my calculus equation here and see if I have all my variables. So do I have L? Yes. Do I have dl by dt? Yes. Do I have an x? Yes. Do I have a dx by dt? Yes. Do I have a y? No. So I'm going to have to do a little bit of work on that one. And this is my unknown. So that's my unknown. So that's good that that's in the equation. If I don't have my unknown in the equation, then I got to pick a different equation. So I'm going to have to do, before I substitute, I'm going to have to do a little bit of work to figure out y. So this is where I'll go back to the original question and recognize that to figure out y, I can use Pythagoras again. So I've got 6.5 squared, that's the hypotenuse, equals 2.5 squared plus y squared. Okay, using this hypotenuse, this side, and my unknown. So a little bit of math here. It's going to be 6.5 squared minus 2.5 squared. You might have punched that in your calculator. That's fine. And it's going to be the square root of that, isn't it? There's going to be a positive and a negative answer. There's no negative here. That doesn't make sense to have a negative y. But Off the top of my head, I think 6.5 squared minus 2.5 squared is 6, I think. So I've done that to figure out that this is 6. So apparently at 2.5 meters, it is reaching up the wall 6 meters high. This is often a case that we'll have to do a little bit of math off to the side to complete my chart. In the example before, I had A, but I didn't need A in the equation, so I never bothered to find it. Like I never bothered finding it because I didn't need it anywhere. In this one, though, turns out that I'm going to need the Y, so I had to do the work to figure it out. Okay, now I've got all of my unknowns can be replaced except for the question I want or the variable I want. So I go through and replace it. So wherever I see L, I'm going to replace with 6.5. dl by dt is 0, so that's going to make that side really easy. 2 times x, so now the x is 2.5. dx by dt is how fast that's changing, so it's 1. The y I just figured out was 6, and dy by dt is my unknown. And now I've got to isolate. So the math's going to start getting easier. Everything's times 0 here, so that's good. This is going to be 5 plus 12 dy by dt. So negative 5 equals 12 dy by dt. So negative 5 over 12 equals dy by dt. And again, in this case, I think I'd like to figure out what that actual number is. So I can punch that into my calculator, and I think I get negative 0.4 rounded 2 equals dy by dt. At first glance, I might panic a bit because I've got a negative, but then when I stop and think about it, that makes total sense because my y in this picture is getting smaller. So it is decreasing or getting smaller by 0.42. So now I'm going to answer the question. So therefore, the ladder, or the top of the ladder, is falling or descending down the wall at a rate of 0.42 meters per second. I've not added the negative here because I said it's falling down the wall, so the rate is 0.46. If I was saying it was going up the wall, it would be a negative number because it's actually going down. So again, recapping, classic calculus question. We have the ladder here, we draw the picture, we write down all of our variables, and then all the related rates, so dl by dt and so forth. Some we may know, some we may not. We find an equation, in this case we use Pythagoras, differentiate it, make sure that we have all the other unknowns, so we needed to do a little bit of math to figure out why, and then substituted to get our answer. Now this is a classic question because I can change all sorts of variables. I could have someone putting the ladder up against the wall, so they would be pushing the bottom in and it would be going up. You could have that. Or you can have maybe a realistic one where you have those ladders that extend. So you could put the ladder and keep the bottom, keep this here and have it extended. So it would look like this. So you put the ladder up like this, so here's the ladder, and you keep that there, and then you extend it, you push this up, and the ladder gets longer. So dl by dt might actually be a number this time because you make it longer. This part would stay the same if you kept the foot of the ladder there. This would go up. This part, the dx by dt, might be 0 because it would stay the same. But this dy by dt would be increasing. So I could say, this is 2 meters away, and you're sliding it up at a rate of 1 meter per second. How fast is the ladder increasing? So the ladder actually does increase in those ones. So there's all sorts of different questions we can have here. So there's a couple of questions from your textbook to try. Really, the key is being able to figure out the formula that you need. If you do look ahead on page 193, some of these questions, you'll see number 3 is the side of a square is increasing, so you'll probably need to use a formula for area of a square. You might need perimeter or something there too, because the question's asking about perimeter. Number 4 is talking about the edge of a cube and a volume, so you might want to use the volume or surface area, so you use those formulas and you differentiate them. 6 is about a circle, except this time the circle is decreasing, and it's talking about area, so you might want to use pi r squared. 7 is similar to the one that we did together with a circle expanding. And then 8, we get the ladder questions. So that's a great. Make sure we can do 8. 9 and 10 are just variations of the ladder. Instead of a ladder, though, it might be a kite, or in this case, you see a picture of a camera following a rocket. Okay, it's still a triangle, but with a side increasing or decreasing, so you can do that. 15 talks about a tree trunk, so you might need the volume of a cylinder. So the point is to go through and try a few of these using related rates, and hopefully you'll be able to solve a couple of problems. Thanks, and we'll see you next day.